You start typing a function name, and before you finish the second word, your editor fills in the rest. Not a snippet, not a template, a neural network trained on billions of lines of code, predicting what you are about to write. This is GitHub Copilot, and by January 2024, it had crossed 1.3 million paying subscribers, already woven into the daily workflow of professional engineers worldwide. But here is the question: how does a system that predicts the next word reliably produce working software? Code is brutally unforgiving. Syntax is strict. One misplaced parenthesis breaks everything. It is executable. You get an objective ground truth result. And it has structural regularity. The same patterns repeat across millions of codebases, which is what makes statistical prediction surprisingly powerful. In this video, we follow a single line of code through the model and back out as a working function. That line is def is prime n. We will watch it shatter into integer tokens, flow through layers of self-attention, and emerge one token at a time as a complete implementation. By the end, you will understand not just what these models do, but precisely why they succeed and where they fail. So what actually reaches the model when you type def is prime of n? Not characters, not words. The model sees a sequence of integers. Every piece of text, including code, is first converted into integer IDs by a tokenizer. Each ID is an index into a vocabulary table of every token the model knows. Def is prime of n breaks into roughly 8 to 10 tokens. Def is primer, copra, n, double copra, a new line, and a 4-space indent. 8 tokens for a single line, and that mismatch has real consequences. The algorithm is Byte Pair Encoding, or BPE. Start from all 256 raw byte values, then repeatedly merge the most frequent adjacent pair until the vocabulary reaches its target size. For GPT-4, that target is 100,258 tokens, 100,000 BPE merges plus 258 special tokens, forming the vocabulary called CL100K base. GPT-4o pushes further with O200K base, nearly 200,000 tokens, giving the model coarser, more efficient chunks and a larger effective context. Once assigned an ID, each integer is looked up in an embedding matrix and replaced by a dense vector. 4,096 dimensions for a 7 billion parameter model, a point in geometric space where similar concepts cluster near each other. Python has a specific problem. A 4-space indent is syntax, not decoration. The tokenizer encodes it as a single token, so the model must predict the correct indentation level to produce valid Python. Get it wrong, and the code does not pass. In a 5-line factorial function, 29 tokens appear. Only 6 carry semantic meaning. The other 23 are syntactic overhead, which is why Python uses roughly 46% more tokens than a BPE-efficient language. Finally, 3 special reserved tokens make Copilot's core use case possible: FIM priority, FIM srefixer, and FIM middle. When you place your cursor mid-file, the tokenizer tags everything before the cursor FIM parier, everything after FIM6, and asks the model to predict what belongs between them tagged FIM middle. Without these 3 tokens, Copilot could only complete at the end of a file. So, one line of Python became a stream of integers. Each integer became a vector, and the model never saw a character or a word. Those vectors now enter the transformer. Inside the transformer, those embedding vectors, 4,096 dimensions each, immediately face a question. Where in the sequence does each token sit? The model uses ROPE, rotary position embeddings, to inject that information. ROPE rotates each query and key vector by an angle proportional to its position, so the model can tell apart A at position 3 from A at position 47 without a separate lookup table. Now, with positioned embeddings in hand, each token asks, which other tokens should I pay attention to? That is self-attention, the engine at the heart of every transformer layer. Each token projects its embedding through 3 separate weight matrices. The first produces a query vector, what this token is looking for. The second produces a key vector, what this token is advertising. The third produces a value vector, the content it contributes if selected. The attention score between position I and position J is the dot product of Q at I with K at J, divided by the square root of D minus K, the key dimension. Softmax then turns those raw scores into a probability distribution, weights that sum to 1. Those weights are used to take a weighted sum of all the value vectors, producing a new contextual vector for each position. But there is a critical constraint. The model generates text left to right, so token I must not peek at anything after it. The solution is a causal mask. The upper triangle of the attention matrix is set to negative infinity before the softmax, making those positions contribute 0. This is what makes the transformer autoregressive. Each position sees only its past. One attention head can only learn one type of relationship at a time, so transformers run many heads in parallel. A 7 billion parameter model typically has 32 attention heads, each with its own Q, K, V projection matrices. One head might track matching brackets across hundreds of tokens. Another might attend to variable names back at their definition site. A third might link function call arguments back to their parameter declarations. The outputs of all 32 heads are concatenated and projected back to the main embedding dimension. After attention, each position passes through a feed-forward sublayer, a 2-layer fully connected network using SWE-glue activation, roughly 4 times wider than the embedding dimension. This is where most of the model's stored factual knowledge lives, not in the attention weights. A residual connection and layer normalization complete one transformer block. The model stacks these blocks, 32 layers for a 7 billion parameter model, up to 96 for the largest. Early layers resolve local syntax, indentation, brackets, keyword boundaries. Middle layers resolve scope, connecting variable uses to their definitions. Deeper layers handle long-range semantics, what a function is supposed to accomplish. Let's make this concrete. When the model is at the return token in def add AB return A plus B and is about to generate A, the attention weights from the current position back to A and B in the function signature spike sharply. No symbol table, no scope stack. Attention recreates variable scope through learned pattern matching. After all transformer layers have run, the final vector for the last token position holds a summary of the entire preceding sequence, filtered through 32 layers of processing. That vector is what the model uses to predict the next token. And in part 4, we will see exactly how. All those attention weights funnel into one moment, predicting the very next token. The final transformer layer outputs a logits vector with one entry for every token in the vocabulary. For GPT-4, that is 100,258 numbers. Softmax turns those logits into probabilities that sum to exactly 1, the full distribution over every possible next token. The simplest strategy is greedy decoding. Pick the argmax, the highest probability token. Greedy is deterministic and fast, but it can trap the model in repetitive loops. A better approach is temperature sampling. Divide every logit by a number t before applying softmax. T less than 1 sharpens the distribution. T greater than 1 flattens it. For code generation, correctness matters more than creativity, so models use t close to 0, often between 0 and 0.2. There is one more trick: top P sampling, also called nucleus sampling. Keep only the smallest set of tokens whose cumulative probability reaches 95% and discard the rest before sampling. This prevents the model from accidentally picking a very low probability nonsense token that would break the code. Now, Each token the model generates gets appended to the input for the next pass. This is what makes generation autoregressive. Context window size determines how much the model can see at once. GPT-4 Turbo supports 128,000 tokens. Claude 3 reaches 200,000. And Gemini 1.5 Pro was demonstrated at 1 million tokens experimentally. The larger the context window, the more of your codebase the model can hold in view while generating. Let's trace "def is I men" token by token. The model runs a forward pass and produces logits. After softmax, def lands at the top by a wide margin. It dominated this position in billions of similar training examples. The model outputs def, appends it, and runs again. The highest probability continuation is prime, then n, then COVID, then a new line, then a 4-space indent. Each of these 8 steps is just argmax over the learned distribution. No grammar checker, no syntax tree, no proof of correctness. The model never proves the function is correct. It reproduces the most statistically likely completion, and if a subtly buggy version dominated the training corpus, it would generate that version with exactly the same confidence. So how did the model learn these probabilities in the first place? That is what Part 5 answers. 4 trillion tokens of training data. One very simple objective, applied at enormous scale. 4 trillion tokens. That number does not feel real until you picture what it means. Imagine every line of code ever pushed to GitHub, every Stack Overflow answer, every language reference, every README, concatenated into a single river of text, and read 4 times over. That is the scale at which modern code models are trained. The most prominent open dataset today is the Stack V2. More than 3 billion source files spanning over 600 programming and markup languages. GitHub's code dataset contributed roughly 115 million files across 32 languages, about 1 terabyte of raw text. StarCoder 2's 15 billion parameter model was pre-trained on more than 4 trillion of those tokens. DeepSeek Coder consumed 2 trillion tokens, 87% pure code, 13% code-related natural language, such as documentation and commit messages. The training objective across all of that data is almost offensively simple. Given everything before this position, predict the next token. That single cross-entropy loss, applied at trillion token scale, forces the model to internalize syntax, standard library APIs, common algorithms, and idiomatic patterns. Not through explicit rules, but as statistical regularities that violations never disturb. But next token prediction alone only teaches the model to autocomplete. From the beginning of a file, real developers place a cursor in the middle of an existing function and ask for a few lines. To handle this, researchers introduced fill-in-the-middle training, or FIM. During pre-training, a document is randomly split into prefix, middle, and suffix. The model receives FIM prefet, the prefix text, FIM suffix, the suffix text, and FIM middle, and is trained to predict the middle span given both sides. This is what powers Copilot's ability to complete code anywhere in a file, not just at the end, and it has been adopted by CodeLlama, StarCoder 2, DeepSeek Coder V2, CodeGemma, and Qwen 2.5 Coder. After pre-training comes instruction tuning, supervised fine-tuning on curated instruction and correct code pairs, which teaches the model to follow natural language requests rather than just autocomplete. But the most powerful training signal does not come from human-written data at all. It comes from running the code. In 2022, researchers introduced CodeRL at NeurIPS, using pass-or-fail unit test results as a reinforcement learning reward signal. If the generated function passes all tests, positive reward. If it fails, negative reward. AlphaCode 2 and the DeepSeek R1 and OpenAI O3 family extend this further. generating chain-of-thought reasoning traces before producing code, and optimizing those traces through RL against test outcomes. This is verified reward, the strongest training signal available because it comes from ground truth. So the training story has 3 chapters. Massive next token pre-training that ingrains language structure. Fill in the middle that teaches cursor position completion, and execution-grounded feedback that teaches the model what working actually means. In the next part, we open the trained model and look at what attention has actually learned about variable scope, bracket matching, and API idioms. We have seen how attention works mathematically. Now, let's ask what it has actually learned to do with code. The most important discovery came from Olson and colleagues at Anthropic in 2022, in a paper called In-Context Learning and Induction Heads. They found that pairs of attention heads implement a simple circuit. If the sequence A followed by B appeared earlier in the context, the model predicts B again the next time it sees A. These are called induction heads, and they are the mechanistic basis for why the model reproduces code patterns it just saw in your prompt. Let's make this concrete with variable scope. Consider def, add AB, return A plus B. When the model generates the token A inside return A plus B, the attention weight from the current position back to A and B in the function signature spikes sharply. No symbol table, no compiler. Attention recreates scope through pattern matching, because names in a return statement reliably follow names from the nearest def line. The same mechanism explains bracket matching. When generating a closing parenthesis, the model attends heavily back to the opening bracket, not by running a parser, but by replaying a structural regularity from hundreds of millions of source files. Now consider API idiom retrieval. In PyTorch training code, 3 lines appear together millions of times. Optimizer.zeroGrad, loss.backward, optimizer.step. Given a training loop context, the model reproduces this idiom with near certainty, not because it understands gradient descent, but because this exact sequence saturated its training data. Few-shot adaptation works the same way. Show the model 2 or 3 examples of a novel API, and induction heads copy that pattern into the continuation, which is the mechanistic reason good prompt engineering works. Now for the honest caveat. None of this is symbolic reasoning. The model has no AST, no type checker, no runtime. When it knows that list.append takes 1 argument, it knows this because that pattern dominated training data, not from first principles. The attention weights look intelligent, and in a statistical sense, they are. But that intelligence is correlation at scale. This matters for where the model will fail, precisely where the training distribution runs thin. Novel interfaces, unusual edge cases, subtle invariants that rarely appeared verbatim in any training file. And that is exactly the territory we explore next. Here is the uncomfortable truth. Benchmarks do not advertise. The model cannot run its own code. It has no compiler, no interpreter, no way to verify what it just generated actually works. And yet, it writes with complete, unwavering confidence. Let's start with hallucinated APIs. The model invents plausible-sounding function names that do not exist. pd.read_excel, missing the second E, syntactically perfect, semantically broken. Studies from 2024 found hallucinated APIs account for up to 15% of all code LLM hallucinations. You only discover the fiction at runtime, when the interpreter throws an authentication. Next, off by 1 errors. Range n versus range n+1 are structurally identical to the model. 1 character, enormous semantic difference. Boundary conditions like the empty list, 0, and negative inputs are systematically underrepresented in training data because programmers tend to post the happy path. Then there is the knowledge cutoff. A model trained through early 2024 does not know libraries released after that date, and deprecated APIs appear with the same confidence as modern idioms. The model is telling you the truth about a world that no longer exists. A fourth problem emerges at scale. Even a 200,000 token context window is not enough for a multi-million line production repository. And the lost-in-the-middle effect means information buried in the center of a long context is retrieved far less reliably than information near the edges. The deepest problem is the confidence illusion. When the model generates a correct implementation, it sounds certain. When it generates a subtly buggy one, it sounds exactly as certain. There is no internal uncertainty signal without execution feedback. What about the benchmarks showing 90+% scores? HumanEval, 164 self-contained toy problems, went from 28.8% with Codex in 2021 to around 67% with GPT-4 in 2023, to past 90% with DeepSeek Coda v2 and Qwen 2.5 Coda in 2024. Impressive, but HumanEval problems are short, isolated, and well represented in pre-training data, raising real contamination concerns. SWE-bench is the harder signal. 2,294 real GitHub issues requiring repository-level edits across multiple files. Top specialized agents in mid-2024 resolved 40 to 55% of those issues. The logical fix is obvious. Give the model a way to run the code and observe what happens. And that is exactly what agentic coding loops do. The agentic loop closes the gap directly. Generate code, run tests, observe output, revise, repeat. Now the model gets the ground truth signal it lacks during pure generation. The test suite either passes or it does not. This is the plan, edit, run, test, observe cycle. And it changes what an LLM can accomplish. The agent reads the task and forms a plan. Which files to touch, which functions to modify, what the acceptance criteria are. Then it edits, creating or rewriting code across potentially many files. Then it runs, executing shell commands, invoking the test suite, calling external tools. Then it observes a stack trace, a failing assertion, a compiler error. Based on that output, it revises and loops again. Tool use transforms the LLM from a text generator into an orchestrator, reading files, writing files, running commands, and searching the web within a single task. Claude Code reads the entire relevant codebase, creates and edits files directly, interprets test failures and build logs, and iterates across multi-file changes until the tests pass. In 2024, Cognition released Devin, integrating a browser, a terminal, and a code editor into a single agent loop. Copilot Workspace brought multi-file, multi-step planning into the GitHub interface the same year. All of these systems depend on large context windows. Holding the relevant portions of a real repository requires at least 128,000 tokens, often 200,000 or more. Which is why every major model release in 2024 and 2025 led with context window expansion. The context window is the working memory of the agent. SWE-bench is the benchmark that measures whether any of this works. 2,294 real GitHub issues, each requiring the agent to navigate the codebase, make correct changes across files, and pass the associated test suite. In early 2023, the best agents resolved fewer than 5%. By mid-2024, specialized agents reached 40 to 55%. Then in 2025, Claude Opus 4, evaluated on the verified split of 500 carefully curated issues, exceeded 80%. That trajectory, from under 5% to over 80% in under 3 years, is one of the steepest performance curves in software tool history. It is not because the language model learned to reason differently. It is because the feedback loop closed. The model now gets to try, fail, read the error, and try again. The same loop every human programmer uses. In the final part, we step back and ask what all of this means for how to think about these tools clearly. We started with def is prime of n and asked how a text predictor turns that into working code. Now we have the full answer. What we have built is the most powerful statistical autocomplete ever created. Not an AGI code reasoner, not a program synthesizer that proves correctness, but a pattern engine trained on billions of lines of code. When the model completes is prime correctly, it does so because that exact function appeared millions of times across GitHub, Stack Overflow, and every competitive programming archive on the internet. It recognized the pattern. It did not prove primality. That framing matters because it tells you exactly when to trust it. Push it to a novel algorithm at the frontier of research, or ask it to reason about subtle concurrency invariance across a distributed system, and its fluency fades. Multi-file correctness, distributed state, truly original design. These remain genuinely hard. But the trajectory is clear. SWE-bench resolution went from under 5% in early 2023 to over 80% in 2025, driven by execution feedback, longer context windows, and reinforcement learning from verified test results. The right mental model for these tools today is a tireless, encyclopedic pair programmer who has read every open-source repository ever written, and who needs your oversight. It drafts the function, scaffolds the module, suggests the refactor. You verify, test, and catch the edge cases it cannot see. That is a force multiplier, not a replacement. And for developers who understand what it can and cannot do, it is one of the most powerful tools in the history of software engineering.